Now that you know how to use Excel to perform the least squares linear regression analysis, you're able to find the slope, the y-intercept, and then write that as an equation of a line, then find the y values for the line of best fit according to the x values from your raw data, and plot that on a graph. You've now developed the tools in order to allow you to start using Excel's built-in least squares linear regression analysis tools. So I'm going to use the example from class 12 that I showed you on how to perform least squares linear regression analysis for the patients versus week data. If you have not already done that problem in your own Excel document, you should open it up now and try to do the least squares linear regression analysis following that video from class 12. Once you do that, you can pick up here from this video in order to do Excel's built-in least squares linear regression analysis. So everyone should have this graph on their Excel document, and what I'm going to do is I'm going to click on that chart. When you click on that chart, remember that you have this plus sign. When you click the plus sign, you may have noticed that there's a trend line. A trend line is exactly what we're trying to do with a least squares linear regression analysis, is we're trying to create a trend for our data. So I'm going to click the check mark for the trend line. Notice because I have 2 bits of information on my graph, it's giving me the option to do my trend line for either one. I want to do my trend line for my raw data. So make sure you select raw data. If you only have one set of data on your graph, this will not pop up and it will automatically do the trend line for the data that you have graphed on your chart. So again, I'm going to click raw data and I'm going to hit OK. And notice, if you see on the screen, there's some dotted lines that formed, and that's my trend line. I'm going to click it and maybe change the color of it so you can see it a little bit better. You can also see it down on your legend on the graph. I'm going to make it a brighter blue color so you can see it a little bit better, and maybe make the weight of it a little bit thicker. So now you can see that trend line. And hopefully what you see is that that trend line actually lines up exactly with the equation of the line that we graphed previously. So from here on out, you should be able to use the trend line instead of actually finding the slope and the y-intercept for when you do least squares linear regression analysis, unless otherwise told. When I click on the trend line, notice another thing you can do with it, and that is you can display an equation on the chart. So that'll give you the equation of that trend line. If the format trend line does not pop up on the side of your Excel sheet, you can always click on the trend line, right click, and click format trend line, and it should pop up. Notice there's an option to click display equation on chart. You can click the display equation on chart and it should automatically put the equation on your chart. And now you can compare the equation that you calculated previously to the equation that matches the trend line that you just put in Excel. Notice how it's the same value. So your slope is 7.6579, 7.658. That's because we rounded. And then plus 29.263 for our y-intercept. And so that should work out the same way because you're doing least squares linear regression analysis, and that's the point of that analysis, is that regardless of whoever does the analysis, you should get the same slope and y-intercept values. The next question that you should be asking yourself is, how do you know that the trend line or the equation, this mathematical model that you developed, fits your graph the best? In order to understand that a little bit better, let's look at a zoomed in view of a singular raw data point in the line of best fit. In order to understand if your line of best fit fits your data the best, you can calculate the coefficient of determination. The coefficient of determination is also referred to as the R-squared value, and it determines the goodness of the fit. So if you see your raw data point, which is the red dot on the graph, compared to the black line, which is your line of best fit, and the data point that matches the x value of the raw data point and the x value of that line of best fit, that same value, you can see that there's an error between the raw data point and the line of best fit. This should be familiar to you because we talked about this graph when we learned how to do least squares linear regression analysis. So if we look at that error for every single data point in your raw data set along the line of best fit, what we do is we take the difference between the y fit, which is the point on your line of best fit, and your individual y value, and we take the difference of that and square it. The reason why we square it is so that we don't have to worry about the raw data point being above or below the line. It makes everything positive. Depending on the data set, you might have a really large error squared or a really small error squared. And so in order to overcome that, so we can have a consistency between data sets, regardless of if it's large data or small data, we do what's called normalizing it. And what happens is we normalize the data by making it fit between 0 and 1. By making it fit between 0 and 1, we're able to have a uniform analysis and understand, regardless of the data set that you're looking at, if the R-squared value or the coefficient of determination falls between 0 or 1, we can see if it's a good fit or a poor fit. The closer it is to 0, the poor the fit is. The closer it is to 1, the better the fit is. If it is a 1, it's a perfect fit. So you can see the equation for that, where we have 1 minus, that 1 minus portion is normalizing the error so that it's all going to fall between 0 and 1. And then we have the summation of the y-fit values, so that value from the line of best fit minus the individual y value from that raw data point, squared, all added together for each individual one of those. And then that's divided by the summation of your average y values minus the individual y value from each data point squared, and then added together for each one. This allows us to normalize the R-square value and have it between 0 and 1. So therefore, we can go back to our data that we were just looking at, and we can determine, is our trend line a good fit or not? So let's click on the trend line, and if you recall, when you're formatting the trend line, when you click the display equation on the chart option, you can also display the R-squared value on the chart. So if I click display R-squared value on the chart, we see that the R-squared value for this trend line is 0.9748, which is a really good fit. So we can kind of assume that, yeah, our linear fit is a good fit. However, you might want to explore other fit options. So on Excel, when you're formatting the trend line, you have the option to choose exponential, linear, which is what we're using, logarithmic, polynomial, power, moving average. And so you can choose through these and see which one has the better R-squared value. If I click exponential, I see that the R-squared value actually increases to 0.9949. So let's get a chart going. I have linear, I have exponential, we had logarithmic, polynomial, and power. And then there was also moving average, but we won't use moving average in this class. So when I click on those options, I can click through them and I can write down their R-squared value. So my linear R-squared value was 0.9748. My exponential R-squared value was 0.9949. My logarithmic value was 0.9095. I'm going to skip polynomial because I want to talk about that one separately. And then I'll check out my power. My power is 0.9535. Then let me go back to the polynomial to talk about that one real quick. So I can click polynomial, my R-squared value is 1. And so you're immediately thinking, that's got to be the right one. What happens with the polynomial is the more you increase the order of your polynomial, you can force it to fit perfectly. That's not a good model of your data because you're manipulating the data to fit the way you want it to fit. So we will not use the polynomial in these classes. You should caution yourself against using the polynomial anytime you're doing this type of fit, and look more at exponential, linear, logarithmic, and power. So I'm going to delete polynomial from my graph and just look at logarithmic, linear, exponential, and power, and then decide which one has the best fit. Looking at these R-squared values, you should see that the best one for this data is our exponential fit. So if I click back on my trend line, I can change it to an exponential fit, and now I have a new equation that fits the model of an exponential function, and that one best represents my data. When you're doing least squares linear regression for future homeworks and for your pump project, you'll be able to plot the raw data, and instead of finding the M and the B like we've done here where we had to add these extra columns and do the summations, now you can just right click your data points and click add trend line, or use the plus sign and add the trend line. But before you just choose the first trend line that comes up, you need to cycle through them, have your equation displayed on your chart and your R-squared value, and choose the one that has the best R-squared value, the R-squared value closest to 1.